opportunity to talk. And yeah, I'm sorry if maybe you can find many black empty space, but I couldn't change it. And so today I'd like to talk about the d-polynomials and explain its property for proper preprojective algebras. This is a joint work with Toshitaka Aoki. So first, I will briefly explain the motivation behind this research. In recent years, a tau tilting theory has become a very active area of research. In simple terms, it is a theory for study many important objects and subcategories within a given category. More precisely, tau tilting theory provides a unified framework for study various objects such as support tau tilting modules, torsion classes, two-term tilting complex, and cluster tilting object, and so on. And under certain nice conditions, it is known these different objects are in one-to-one correspondence with each other. Furthermore, a recent important discovery is that from these algebraic structures, we can construct some important combinatorial objects like simple shell complex, fans, and portals. Because these objects are quite classical and has been studied extensively, by analyzing them, we can gain a deeper understanding of the original algebraic structures. This connection creates new and fruitful links between algebra and combinatorics and provides new insights. Following this direction, in this talk, we introduce new notion called d-polynomial for tau-rigid modules. They are regarded as a classical analog of the classical notion called f-polynomial and h-polynomials. We can define these d-polynomials for any finite dimensional algebras, but in this talk, we mainly discuss for preprojective algebra, in particular type AN, and explain its property and explain the connection with classical Euler polynomials. Okay, so let's begin with the basic definitions. Let A be a finite dimensional algebra, and the number of indecomposable direct summands of A is n. It means if we describe A by quiver with relations, the number of the vertices of the quiver is n. And we denote by mod A the category of finite dimensional right A modules. And the project A denotes the category of finite projective A modules. So first, take module M and the projective module P. We call module tau rigid if it satisfies this condition. Namely, this tau is AR translation, and we have no morphism from M to tau M. Quite simple definition. And we call a pair module M and projective module P tau rigid if M is tau rigid, and we have no morphism from P to M. And tau rigid A denotes a set of basic tau rigid A modules, and tau pair A is a set of basic tau rigid pairs. It's better to write tau rigid pair, but for simplicity, let me write tau pair A. And we call a pair support tau tilting if it is a tau rigid pair and satisfy this condition. Namely, the number of indecomposable direct summands of M and plus P equal A. And it is known this number is at most A. Namely, at most N. Then we can also define this set, tau rigid pair J. This is a set of tau rigid pair satisfying number of indecomposable modules M and P equal J. So this takes from 0 to at most N. So let's check with a simple example. Let's check this definition with a simple example. Let A be a following path algebra type A2. As you know, the algebra has the following shape, consists of 3 indecomposable modules. And for simplicity, we denote this pair just by module if projective part is 0. Similarly, if module part is 0, we just denote by projective, but to distinguish this part, this case, so just put shift 1. Then let's check these two sets. Tau-rigid pair 1 consists of 1 indecomposable module. So these 3 indecomposable modules are tau-rigid, so can be regarded as a tau-rigid pair of this case. And these projective also a tau-rigid pair because this is satisfy this condition. Then tau-rigid pair 2 consists of any element of this one is just 2 indecomposable module. For example, this is a tau-rigid pair module. So namely, this is a tau-rigid pair like this. And in this case, this is a tau-rigid pair like this. In this case, this is a tau-rigid pair, this one. As you see, this consists of 2 indecomposable modules. So this is a element of this tau-rigid pair too. And for us, very important fact is these tau-rigid pairs form a simple shell complex. So this zero simplex is tau-rigid pair 1. Namely, this tau-rigid pair 1 is union of indecomposable tau-rigid modules and indecomposable projective. Generally, J simplex is defined by the tau-rigid pair J plus 1. Then this set form a simple shell complex called G simple shell complex. So recall by simple shell complex, we mean a collection of subset of these base set and closed under taking subset. Because element subset of tau-rigid pairs is again tau-rigid pair, so it is a closed under subset. So let's check with this previous example. So we already know these tau-rigid pairs. Then the structure of simple shell complex has a following shape. Each vertex corresponds with the element of tau-rigid pair 1. Edge corresponds with tau-rigid pair 2. More big example is type A3, and similarly, we can check tau-rigid pair 1. This is consists of 1 indecomposable module. And similarly, tau-rigid pair 2, tau-rigid pair 3, like this. Then the shape of G simple shell complex has a following one. So similarly, each vertex corresponds with element of tau-rigid pair 1. And H provides a corresponds with the element of tau-rigid pair 2. In this case, the face, for example, this face corresponds to this element. So similarly, this face provides this one is this face. So from this information, we can get the shape of the simple shell complex. Actually, we can give a natural realization of this simple shell complex, but in this talk, we don't discuss such a geometric realization now. So anyway, for a given algebra, we can define simple complex, which come from the tau rigid pairs. And for a given simple complex, we can define f vectors and h vectors, which are quite classical. So let me briefly recall this one. F vector is just a number of simplex. F minus 1 is formally just put 1. Fj is just a number of element of J simplex. In our case, this is a number of tau rigid pair of J plus 1. And F polynomial is defined by using these vectors. So namely, this is a polynomial whose coefficient is given by F vectors. So this is a start from Fn, and in this case, the minus 1. And similarly, F0 is 1. And H polynomial is kind of a brother of F polynomial. This is quite similarly defined, but this H vector is plays a very important role. We can define H polynomial by using F polynomial, but we can also define H vector by using this F vector, so whichever is fine. So anyway, F polynomial and H polynomial has a kind of same information. Namely, if we determine F polynomial, we can also determine H polynomial, and vice versa. So let me briefly explain these notions. Let me let A be the following quiver and relations. This is one of the important algebra called preprojective algebras, type A3. So namely, we can consider the path algebra, and we add new arrows into the opposite direction. So namely, arrow has always double quiver, and require some commutative relations. In this case, the simple complex has a following shape. Again, each vertex corresponds to the tau rigid pair 1, and similarly H, and similarly face. In this case, we have a F polynomial like this. So namely, if you count the number of the face, we get 24, and H is 36, and vertex is 14. And from this F vector, we can get the F polynomial, we can get the H polynomial like this. Just a simple calculation. The result is this one. And this H polynomial is quite important because this is nothing but classical Eulerian polynomial. And this is always true for preprojective algebra, and we will discuss this connection later again. So now we explained new notion called d-polynomial. D-polynomial is defined as follows. We consider the all tau rigid pair and consider the dimension as a k-vector space of M, only this module part. And the degree is defined like this. It's equivalent to say we consider the polynomial, and the degree of n minus j, the coefficient of degree of n minus j is defined as follows. We consider the all j minus 1 simplex, so namely tau rigid pair j, and for this module, we just count the dimension of M and take the sum for this dimension. So it means just count the dimension, so not so difficult definition. So let me check this definition again. So In this case, we already know tau rigid pair 1, tau rigid pair 2. So in this case, just check the dimension. Dimension 1, dimension 1, dimension 2. So the sum is 4. And this number provides a coefficient of this polynomial. In this case, dimension is 3, 3, 1, 1, and 0. So this is 8. So we get this one. So this is the polynomial. So we only focus on module part, not project part. Okay. So then let me briefly explain why we consider this notion. This is one important algebra called Brouwer tree algebras. They are both Brouwer tree algebra, and if we calculate the shape of the simple shell complex, this provides this simple shell complex, and in this case, this provides this simple shell complex. As you see, this shape is different. Nonetheless, sometimes it provides f polynomials and same f polynomials and so h polynomials. So in this case, they are different, but these their h polynomials is same. On the other hand, if we try to calculate the d-polynomial, we get different polynomials. So in this sense, the notion of d-polynomial focus on more homological quantities. And the aim of this talk is explain these d-polynomials, in particular for preprojective algebras. This is just because of the time. We can also discuss path algebra, but in this talk, we only focus on only for preprojective algebras. Okay, so now we explain some techniques to study the polynomials. So let me briefly recall the important result by Hassel. Let A be a finite dimensional algebra. M is tau-rigid A module. Then we have some finite dimensional algebra denoted by Cm, and it satisfies this condition. And we have a bijection between the tau-rigid pair containing M and tau-rigid pair Cm. So what does it mean? It means this condition means this finite dimensional algebra is smaller than original algebra A. If we described this algebra by equivalence relation, this number is the number of the vertices of the quiver is smaller than original algebra A. So this is a simpler algebra. And this theorem says tau-rigid pair containing of M can be controlled by such a small algebras. By using this result, we can define this result as follows in terms of simple shell complex. So namely, by link M, this is described like this. For more precisely, this is a subset of simple shell complex consisting of all pairs and P such that M plus N and P is tau-rigid pair. What does it mean? So let me consider the case of this 1, 2, 3. So for example, consider this case. Then what is a link in this case? It means this is a simplex containing of M. and this is also simplex containing of M. So in this case, the link is described this green part. So namely, the simplex containing of M is this part. So this NP is in this case this part. And actually this part is again given by the finite dimensional algebra, in this case type A2 preprojective algebras. So namely, this subset is controlled by this small r algebra. So more precisely, we can get the following isomorphism. This link is given by some small as a simplicial complex of this small algebra. By using this fact, we get the following key observation. This d-polynomial can be calculated as follows. So just consider the indecomposable tau-rigid M and just multiply these f polynomials of the link M. So again, let me explain this meaning. So consider the same example. We already calculated this d-polynomial, but this equality explains another way to calculate. For example, focus on P1. You can find P1 is here and also here. So one time in this set and two times in this set. If we consider this PP, namely finite dimensional algebra corresponding to P1, then this is a rank 1 algebra. So this is just simple algebra. And in this case, a polynomial is t plus 2. Then this equality means this dimension P1 multiply t plus 2. It means actually we calculate this P1, this is correspond to this coefficient. And this 2 times correspond to this one. So in this way, we calculate about P1 by this equality. So similarly, if we consider P2, we consider this one. No, sorry. And in the case of 1, this is a given. So in this way, we give another way to calculate. Maybe it's too small, so it's a little bit complicated, but more bigger case is simpler. For example, consider this 1, 2, 3. You can find this is a 1 and 1, 2, 3, 4, 5, and also 1, 2, 3, 4, 5. So in this case, we get the dimension 1, 2, 3, and this polynomial is 5 plus 5. So by consider this polynomial, we can calculate about these purple lines. And similarly, we can consider this for each indecomposable project. So this is just a change, which just change the way to calculate. And from this viewpoint, it's natural to consider some equivalence relation on indecomposable tau-rigid A module, denoted by M and N, which is called compatible with links, if these links is isomorphic. Even if M and N is sometimes not isomorphic, but it provides the same links. Then we denote this bracket, the equivalence class of M under this equivalence relation. And this big D is just the sum of all element of M and consider the dimension of this X as a K vector space. Then if M1 to MR is complete representative of the indecomposable tau rigid under this equivalence relation, then we get the following equality. Namely, we need to, in general, we need to consider all F polynomials for each M, but because sometimes it provides a same link, so it means that about the element belongs to this equivalence relation, they provide the same link, so we can just formulate as follows. This we will again visit it again this equality later. Okay, so from now we consider why preprojective algebra and explain why we consider preprojective algebras. So let me to be a thinking quiver. Thinking means here just type ADE for simplicity. And one important fact is actually in the case of preprojective algebras, this does not depend on the orientation of the quiver Q. Namely, we don't have to deal with quiver, but it's enough to deal with graph. Thinking graph is fine. But it's usual to deal with quiver in the case of quiver representations. So I use the quiver, but thinking graph is also fine. And for given thinking quiver, we can define the Coxer group. This just depends on the graph. So type AN is the, as you know, symmetric group. And we can consider the Coxer complex. One simple way to define Coxer complex is consider the file chambers, and we consider the sphere. If we consider the intersection with sphere, it provides a naturally simple shell complex. So for example, if we consider this three-dimensional case, a cone, then the intersection is described like this. Then this vertex is zero simplex again, and the edge is one simplex, and this face is two simplex. So similarly, even higher case, we can define Coxer complex. And for given element W, we can define a descent. This is a set of simple generators, Si, which makes the length become shorter. So namely, if we apply, if we consider the multiplication of simple generators for this W, always length is shorter or longer, become shorter or longer. If this element becomes shorter, we call this the descent. It means this element is at most this number. And this small des is a number of descent. So I should say now, this is at most this number. So the number of the vertices of the quiver. And this W Euler number is the element number of the element W whose descent is J. It takes from 0 to this number. And W Eulerian polynomial is a polynomial whose coefficient is given by these Eulerian numbers. Another explanation of this polynomial is in terms of weak order. So namely, if we consider the Hasse-Kuiper of weak order, then this descent is interpreted as outgoing arrows. So you can see, for example, focus on this element. We have only one outgoing arrow. And this arrow is correspond to the number of this one. So for example, in this case, we have two outgoing arrows. And in this case, 0 outgoing arrow. And this number corresponds to this coefficient. So namely, in this case, we have only one vertex whose outgoing arrow is 2, so this is a 1. And in this case, these 4 elements has a 1 outgoing arrows. So namely, we have a 4. And in this case, 1. So similarly, using this Hasse-Kuiper, we get this polynomial. And you might remember this polynomial was already appeared. Actually, this is can be realized as the H polynomial of the preprojective algebra. But before this, I'd like to mention another important fact. This H polynomial of the H polynomial of the Coxer complex coincide with this W Eulerian polynomials. It's a quite classical fact. And for us, important point is this quite classical notion is related to the recent notion of the representation theory. So namely, if we consider the Dynkin-Kuiper and consider the preprojective algebra, then the G simplicial complex is nothing but Coxer complex. So in this sense, this G simplicial complex is quite a natural object in this sense. In particular, by the previous fact, because H polynomial of pi, I should say write this simplicial complex is H polynomial of the Coxer complex. And because of this fact, this is given by Eulerian polynomial. In this sense, we can say H polynomial of preprojective algebra is Eulerian polynomial. Then it's natural to consider d-polynomial. How about the d-polynomial of preprojective algebra? And we will explain this one. And to understand this, we need to understand the compatible object on preprojective algebras. So let pi be the preprojective algebra of Dynkin-Kuiper, and for each vertex, we consider the full subquiver of Q, removing the vertex L. For example, if we consider this one, type A5, then this, for example, take 4. Just remove this one. Remove this vertex and associated arrows, then we get this quiver. It's not necessarily connected, but it's fine. We get another 2 quivers, which are type A3 and type A1. Then we give one important fact. For each L element of submodule of this indecomposable projective, so I mean this is a idempotent corresponding to the vertex, then these submodules are tau rigid module. And the more important point for us is they are compatible with links each other and isomorphic to the this Coxeter complex corresponding to this quiver. Namely, if we consider the submodule of this one, then the link is always isomorphic to the G-simplicial complex of indecomposable project. And in this case, it's easy to get the isomorphism to the Coxeter complex. So in this sense, in terms of the previous notation, the equivalence class of this indecomposable projective is nothing but all submodule of this indecomposable project. By as a summary of the previous observation, this d-polynomial can be calculated by using for each indecomposable tau rigid module, but it's quite hard to, in general, to determine the link for each indecomposable tau rigid module M. But in the case of preprojective, we get quite nice equivalence class, namely each tau rigid module provides the same links for each submodule of indecomposable project. And we only need to calculate the dimension of this submodule. Because this F polynomial is nothing but Eulerian polynomial, which is well known. So to determine the d-polynomial, this is just one last step. We need to calculate the dimension for all submodule of indecomposable project. So we need to calculate this one. And from now, we need to fix the type because this heavily depends on the type. We can also calculate type Dn, but it's more complicated, and the type E requires some computer analysis. And one important point for type An is we give the quite explicit description of indecomposable projective. Namely, if we fix a vertex L, then indecomposable projective is given as follows. Like this, it means for each vertex, we just put vector space, one-dimensional vector space, and for each following arrows, just consider the identity, then we get the representation. This is a shape of indecomposable project for the case of type N. For example, let's consider type A7, then indecomposable projective, usually described P5, has the following shape. So this is a top, and this is a soku. The top is a 5, and we have a 2 like this. So just omit the orientation. And in the case of, for example, indecomposable projective of associated with 7 is this shape. And 2 is this shape. So always such a square shape. And because of this nice shape, we can calculate all submodule and also their dimensions. To consider this, we need consider the lattice path. So this is a path in the 2 that takes only step east, so namely right-hand side, and north, upper side. And this is a set of by LST, the set of lattice paths, sigma from 0 to ST. So let me briefly explain. For each L, we consider this lattice path. First, it looks complicated, so I just remove this inside. This is just lattice path. So this is just L and N minus L plus 1. So it's not difficult, but why we consider this lattice path? This is because this lattice path encircled indecomposable projective inside like this. Why we consider this lattice path? This is one simple but interesting point. For each lattice path, we can get the submodule of this indecomposable project. So let me explain for this type 7, A7, and this indecomposable projective. So what we want to do is determine all submodule of this indecomposable project. For this purpose, we consider this lattice path and consider the path from this point to this point. For example, consider this is a lattice path. Then let's focus on this bottom part. Then we can get this part. This is nothing but this one, and this naturally can be regarded as the indecomposable module. So namely, this is just put one-dimensional vector space. This is a quiver representation. So namely, this lattice path provides this indecomposable indecomposable module, and which is tau rigid. For example, in this case, by taking this part, we get this module. And in this case, we get this one. So in this way, for each lattice path, we get the indecomposable module, which is tau rigid. So as a summary, we can get the following bijection. For each lattice path, we get the indecomposable tau rigid module, which is a submodule of this indecomposable project. And this is nothing but the equivalence class of this project. And what we want to do is calculate the dimension for each indecomposable module. This is naturally regarded as the area of this one. So namely, this you can find 1, 2, 3, 4, 5 squares, and this is nothing but the dimension of this one. So in this case, what we will do is to determine the dimension of this module, we just check the number of squares of this bottom part. And this is just a purely combinatorial question, and it is already known. The answer is given by these numbers. This is some famous numbers, and it has another interpretations. So as a summary, we conclude that the polynomial for type AN is described as follows. So some numbers and the multiplication of the Eulerian polynomials. And this is just a table of these d-polynomials for some small numbers. And we can also find the maximum numbers of these d-polynomials has some connection with a classical combinatorics, namely this highest degree, so this n minus 1, the n minus 1 is nothing but the dimension of the support tau tilting modules. This number is a green one, is actually provides a La numbers. And we don't know why we get this number. So namely, it's also interesting to give a direct connection between these numbers and these classical numbers. Why we get such a connection. Okay, so finally, we give us some connection with classical work by Euler. So he studies exponential generating functions of this Eulerian number, and it has some beautiful closed form. So namely, this exponential generating function has following closed form. And because this Eulerian polynomial is interpreted as a H polynomial, it's natural to ask the case of D polynomials. And surprisingly, it also has some beautiful closed form. So namely, if we replace this to H polynomial to the D polynomial, then we can again get some closed form. It's actually used this equality. But we get some sketch of this proof, but it's not so important now. So finally, I just give some questions. So what kinds of generating functions can we realize F polynomials, or H polynomials, or D polynomials of algebras? So in this talk, we focus on preprojective algebras and its H polynomials and D polynomials has some nice generating functions. But of course, there are so many algebras, and sometimes we maybe get some nice, beautiful generating function from algebras. And we don't know anything about the other case. But we already know the case of path algebra. It also has some nice generating functions. And another question is, what type of properties of algebra are captured by generating functions? As I said, for preprojective algebra, we get some nice generating functions. And in the case of path algebra, we can also get some beautiful generating functions. But in the case of preprojective algebras, we get exponential generating functions. On the other hand, in the case of path algebras, just usual generating functions. We don't know what kind of properties provide this difference. So generating function, we hope, provides some shows some property of algebras. And these questions probably no one try to consider these questions. So we are very happy if you are interested. So thank you very much for your attention.
So thank you very much for your very nice talk. Thank you. Are there any questions or comments? Maybe I start with some small question.
Mhm.
Uh, uh, in one of your example, you speak about the two kind of the polynomials. I means h polynomials and f polynomials, and you say that f polynomials have some homological property better than h. Can you explain about what kind of the homological property you mean?
Ah, I see. Yeah, this is just so in the case of simplicial complex and the F polynomials and the H polynomial is just a focus on the structure of simplicial complex. So they don't know, they doesn't say anything about the homological uh, property, namely about the dimension or any modules. But in the case of D polynomial, in some sense, measure the quantities of the dimension because we just calculate the dimension.
You mean
So
the dimension of the,
yeah, for example, we can get if consider the algebraic and the A maybe B and the A B B A. But we can, for example, consider the AB square BA square and the AB n and the BA n. Then the composition series is like uh, longer. Nonetheless, these uh, algebra provides the same F polynomial and H polynomial. So namely, even algebra is quite big, they provide the same F polynomial and the H polynomial, so cannot distinguish the difference.
ah, ah,
Yeah.
ah. Mm. And another question is about the connection between cluster algebra. In type A of preprojective algebra, is there some connection to the cluster algebra?
Yeah, in the case of cluster algebra, instead of a preprojective algebra, path algebra has a quite strong connection with cluster algebra. Namely, if we maybe we already, oh yeah, this is actually nothing but the cluster complex.
Ah,
And
ah,
yeah, so because yeah, probably I should mention this cluster algebra and the cluster tilting object has a very important connection. More precisely for path algebra, we have a bijection between cluster tilting object and the uh, clusters. So, and the cluster tilting objects has a bijection between the support tau
support
tilting module.
module.
So, yeah, it provides yeah same structure.
Ah, yeah, yeah. And the other question, in a tilting case, there is a well-known simplicial complex due to Riedemann and Schofield, and it's the same definition or is it different?
Ah, very important point. Actually, this is a slight generalization of the classical tilting case.
Mm.
Yeah, because tilting module is some special support tau tilting module.
Yeah, yeah, yeah.
In some sense, so some part is oh, yeah, some some part of this picture is a tilting module.
Yes, yes.
Yeah.
So it's a generalization of that simply complex.
Yeah, yeah.
Mm. So thank you very much. So if there is no question, let's thank the speaker again. Thank you very much
Thank you very
for your very
much.
nice talk. Thank you.